So welcome back. Tools of Operations Research. I've gotten a number of emails from some of you asking questions about Assignment 1, so I figured we'd take a little bit of time tonight and go through that. So we'll kind of review the data mining aspect and then kind of look at a little bit at the assignment and talk about how to go about doing it. It'll be due obviously later tonight. And then from there we're going to move on. The next major topic we'll discuss is short-term forecasting, which is predicting future events or future values of a time series. And then hopefully we'll get through that relatively quickly in about an hour or hour and a half. And that'll leave us some time to start talking about linear optimization at the end of tonight. So we'll just see how far we get. So, and this lecture is being recorded and will be posted later. So if you need to go back and re-listen or try to learn again, that'll be available. So data mining, the things we talked about last week, just as a general overview, data mining is used for two main purposes. Its goal is to find a pattern in a set of structured data, and structured data meaning that you have records that all have common fields that they have values for, something like a database. And what we're trying to do is find a pattern in that data that would help us either understand aspects of the data, understand the pattern, or use that pattern to either predict or classify field values for possibly future records. So I think the example I gave last week, if we had a database of student information, students' gender, age, number of hours they were taking, and so on and so forth, we could try to look for patterns in that data using a data mining algorithm, and either use that to understand that pattern, understand, who tends to graduate versus not, or who tends to, have a higher GPA. Is there a pattern to that kind of a student, and so forth. Or we can predict or classify new data. So we might be interested in looking historically at students who did and did not graduate and different classifications of them, again, gender, age, and so forth, and try to use that to predict for a current set of students whether or not they will graduate or not, or whether they're likely to graduate or not, based on a pattern we've identified through data mining in a set of historical student records. Okay, so either aiding, understanding, or predicting or classifying new data is the overall goal of data mining. We talked about the two different data value types, one of those being categorical, where the values are simply names of classes or names of groups or names of categories that the data can fall into. And then numeric data, which is obviously numbers. They could be whole numbers, they could be fractional or decimal numbers, but any kind of number. Okay. And data mining algorithms themselves, of which we talked about 3, they might have restrictions on what they can do. So they may only be able to predict numeric values, or they may only be able to classify or predict categorical values. Okay, so some algorithms are limited into which they can be used for. And then further, some algorithms could be restricted on what other data value types they allow. So for example, one of the data mining algorithms we talked about was multiple linear regression. It can only be used to predict numeric values from other numeric fields. Okay, it can't work with any categorical fields. Okay, and the reason is it relies solely on mathematics, multiplying and adding things together, where it wouldn't make sense to add or multiply or take averages of categorical fields. Right, there's no order to them, or if there is, there's no inherent value to the difference between one value and another. Okay, so everything has to be numeric so that it can add and subtract, multiply, and manipulate the data in that way to find a pattern. Okay. And then finally, the way we evaluate or compare data mining algorithms is to either examine their error rate, so in terms of classifying records, where you're trying to classify a categorical field, whether, say, a student will graduate or not graduate, the error rate would just be the percentage of errors made, the percentage of predictions or classifications that were incorrect. Okay, In terms of a numeric prediction, you can actually take the difference between the predicted value and the actual value for the data you have and take something like the average error across all your records, or the sum of squared errors, or things like that, and use those kind of error metrics to gauge how well the data mining algorithm is done. Okay. The other main thing we use to evaluate data mining algorithms is something called a lift chart, which really takes a look at one, especially where classification is concerned, it takes a look at one specific category value. If you're trying to predict the students who do graduate, the lift chart would show you how well the algorithm does at predicting the graduating students, okay, over an average guess. And an average guess would say, well, if 80% of students graduate, then I would just predict everyone graduates and expect to get it wrong 20% of the time, or get it right 80% of the time. So that would just be a very naive algorithm, or a naive way to classify students. So a lift chart would say, how much better does a data mining algorithm do at predicting who graduates over that naive approach? Okay, and graphically it demonstrates that with just a simple line chart. Okay, so we'll take a look at a couple of examples, see how that works. So let's go into Excel, find a database file we can use as an example. Okay, sure. So we'll address some of the questions from the homework as well. Let's see here, chapter 6. So we'll use the airfares database or data set as an example. Okay. So this airfares data set is a list of flights, airline flights from some city to some other city. It involves several fields, which different aspects of that flight. For instance, the distance flown, so that just the number of miles between the starting and ending point. It lists things like the median income in the starting city and the ending city, populations, as well as some things which are categorical, such as whether or not the destination city airport is categorized as a free or controlled slot, which has to do with how congested the airport is expected to be, and as well as the gate type, whether it's free gate or constrained gate airport, and so forth. And then at the end, what we have is the airfare, the cost of a flight from that particular city to the other one, and so forth. Okay. And what we're interested in is, can we use data mining algorithms to find a pattern to this data that would help us predict the airfare, okay, for some city to some other city. Okay. Now, to do that,
I have a quick question.
Yeah, we have a question.
So say we chose K nearest neighbor. Could we have just done a classify?
Okay, so the question was, using an algorithm like K nearest neighbor, which can be used for classification or prediction, could we have used that here as a classification?
Without transforming the...
Sure. In particular, whether we use a classification or a prediction type algorithm depends solely on the field you're wanting to predict or classify. And in this case, it's an airfare, which is a numeric result. Okay. Yeah. So a classification algorithm would say, of all the possible values I see here, I'm going to guess one of those for all the records. Okay. That's how I'm going to classify. And in this case, that wouldn't really make sense. There's something like, I don't know, maybe 100 or 200 different airfare amounts, right? So 100 to 200 categories, if you wanted to think of it that way, doesn't really make sense. These are just numbers, right? We would want to predict a numeric, just dollar and cents amount. Now, getting to another part of your question, sort of underlying what you asked about using a classification algorithm so that we could use categorical fields otherwise. That, whether or not we can use fields that are categorical, like slot and gate, versus fields that are numeric, like distance and whatever this PAX, passengers. Okay. Whether we can use those two different types depends on the algorithm itself. Particularly K nearest neighbor, I think requires all numeric fields. Okay. Okay, multiple linear regression requires all numeric fields. I believe classification regression trees can use fields of both types.
Okay.
And other algorithms that we didn't discuss may be constrained or not on what they can use. So those things just depend solely on the algorithm you use. Whether you're doing classification or prediction depends on which field you're trying to
That's where I was trying to
understand or guess or predict.
I was trying to classify.
I see, yeah. So in this case, we have to use prediction algorithms because we want to predict the airfare, the dollar and cents, the numeric airfare amount. Okay. So the first thing we would want to do is take a look at all these fields. And really, first we would want to decide which fields do we want to include in the model. That is, which fields do we think are important to predicting airfare. Okay. In particular, the first 4 fields involve the name or a code, airport code, I guess, for the start and end city. Okay. In the homework assignment, I told you not to use these 4 fields. Okay. I didn't give you an explicit reason. The reason is it wouldn't be useful to build a model that relied on city names because that model would never be able to predict airfare for any other cities. If it tried to predict the airfare for Oklahoma City and none of the data involved Oklahoma City, that would be a brand new data type that it would have no idea how to compare it to the existing data. For example, K nearest neighbors wants to find the K closest or most similar records, where if you were trying to predict a new record with a city name that you've never seen before, how would you know how similar or dissimilar it is to all the other records? Okay. And it just makes sense that if we want to build an algorithm, we'd want it to be, ignorant of the names of the cities. We'd want it to be based on things like city incomes or city populations, because in that way you can pick any city in the world you want to predict an airfare for, and as long as you know its income, median income, population, things like that, the model or the algorithm could do the work. Okay, so that's why we're going to leave off these first 4 fields. That is, we're not going to include them as inputs to the data mining algorithm. The other fields, so coupon, new, those 2 appear to be numeric. Vacation and something for Southwest are definitely categorical. Right? Every record is either a yes or a no for each of those. Particularly if we're going to use, let's say, K nearest neighbor as the algorithm, we will need to first transform these 2 fields, okay, from categorical to numeric. The process for doing that is called dummy variables, okay, and we'll demonstrate that in just a moment. The next several fields all look numeric until you get to the slot and gate fields, which again are categorical. Every record has just a named category it falls into. In the case of these 4 fields that we're going to transform, they all have 2 categories apiece, 2 possible answers or 2 possible values, okay, which doesn't particularly matter, just something to keep in mind. But those are the 4 fields we'll need to transform. The way
Can you just change them to 0 and 1s? Like
yeah. So the question is, could I come through here and just say vacation no's or zeros, yeses or ones? That makes them numeric. You can certainly do that. It's not impossible, and it might be the right thing to do. Particularly, that's not how dummy variables work. Okay. And that's generally not the best practice. Okay, let me show you how dummy variables work, and then I'll address that, why it's different. Okay, so to transform data using the analytic solver platform model or software, we'll use the transform button, transform categorical data, create dummies. Okay, and you'll notice there are other ways to transform categorical data that we didn't discuss, but this is the one most common, most conventional way to do it. So we'll do that, create dummies. It's going to give us a listing of all the fields, and we're just going to simply select off the ones we want to convert or transform. So vacation, Southwest, slot, and gate. And it will transform each one all at once for us. Okay. So I'm going to scroll to the right here. You'll see how it transformed them. So particularly, it took the vacation field and converted that to two fields. One of those is for the records that had a no for vacation, and the other field is for those records that had a yes for vacation. Okay. Now, where we have just two possible values for a category or for a categorical field, you probably could have just inserted zeros and ones as opposed to this, and it probably would have been fine. Where you have multiple values is where dummy variables are more useful, because at this point every record has 1 1 and 1 0 in these two fields. That is, it's either a vacation no or it's a vacation yes. The nice thing about that is between two records that are different, they differ by 1 in both fields. Okay? If you had, 5 possible values for vacation, okay, then the difference between two records that had different vacation categories would again be 2, okay, because you'd have a 0 where you had a 1 and a 1 where you had a 0 between the two different records. Okay. If you didn't follow that, that's okay. I'm trying to just explain. If you had made up values like 1, 2, 3, 4, 5, then the difference between two records could be 1. That is, it could be the difference between 1 and 2. It could be 4. The difference could be 4. That is, you have a record with a value of 1 and a record with a value of 5. So you've sort of made up or fabricated the fact that some records are more different than others by fabricating values. Dummy variables don't have that problem in that every record will differ by 2 from another record. Okay, so a no record versus a yes record, so like these two here, differs cumulatively by 2. There's a difference here of 1 and a difference there of 1. That's more equal among all the differences when you have 3 or more categories. Just another question? Oh.
So,
Let me let her. She had her hand up.
So if you use the dummy variables and you use the multiple linear regression, does that mess up, like having the zeros, does that mess up that algorithm?
Sure. Yeah, that's a good question. So the question was, for those who couldn't hear it, using an algorithm of multiple linear regression, which is going to multiply and use different values from fields, would that mess up given that you have fields that have a value of 0? And the answer is no. 0 multiplied by something will be 0, but that's fine. That doesn't necessarily invalidate the model. Now,
what is the advantage of fabricating the data?
okay, so the question is, what would be the advantage of fabricating values for the data? So assuming a value of 1, 2, 3, 4, and 5 or something like that. I guess there's not really an advantage to doing that unless you know or want to assume that some records are more different than others. That is, you want the difference between them to have meaning. Okay. One possible example is if you had a categorical field of, say, priority, and the possible categories are low, medium, and high. Okay. You might want to use values like 1, 2, and 3, because at that point you might want to say low and medium are different, but low and high are more different than one another. That is, there's technically more meaning there because they're at opposite ends of a spectrum. That is, the order also implies that being different by 1 or different by 2 in that order is important. So that might be a case where you would do that. I think, I'm not ready to demonstrate it, but I think one of these other options can do effectively that, something like this category scores. You basically assign a value to each category, like 1, 2, 3, and 4, or something like that. So that's possible, and maybe applicable in some cases. Okay, so we took these 4 fields that were categorical and effectively converted them to 8 numeric fields of zeros and ones.
So, like, do you need to update your data definition to represent this in some way?
When you say data definition, do you mean this sheet here?
Data dictionary.
Okay.
Sorry.
Yeah, so the question is, should we go back to this data dictionary and update it? I don't expect you to do that as part of this class. probably in the real world, you'd want to document it somewhere that I use dummy variables as opposed to scoring or fabricated values, and the reasons why. Okay, so now that we've converted the data, we have all numeric fields, except for these 4 that, again, I'll ignore. So now that I have that, the next step, always the next step, for every data mining algorithm is to partition the data. Okay, and as long as I'm on this sheet here and just select partition and standard partition, it'll do the right thing. Okay, it'll find how many records there are and randomly put them into 2 categories: one for training data to build the model for the data mining algorithm, and one validation set of data to validate that that model is doing well. Okay, that we're not overfitting or finding a pattern that shouldn't really be there, or exists only in the noise or the randomness. Now, for the fields I'm going to use, I'm going to leave out those first 4 fields, okay? Because I know city names and city codes aren't going to be useful, and in fact they're not numeric, so I wouldn't be able to use them anyway. I'll just leave them out of the partitioned set of data. You could do that here, or you can do that later. There's not a right or wrong way to do it. But I'll just let it randomly put 60% of those rows in training, 40% of them in validation, and only include the fields that I'm going to use as inputs to the model. Okay, so now I have that done. Now I can actually run or execute one of these data mining algorithms. Again, we're going to do a prediction algorithm, not classification, because what we want to do is predict airfare, which is numeric. So we'll use multiple linear regression to start with. Okay, so that's a prediction algorithm, and what we need to do is we need to tell it first which fields are the ones that we want to use as input to the model, that is, want to find a pattern to, and then which field, airfare, is the output that we want to predict. Okay, so basically what we're saying is we want to find some way to combine the values from these fields, multiply them by some number, add them all up, and use that as our prediction for airfare. Okay, that's what the multiple linear regression algorithm does. Yes?
So if you wanted to select a weight variable, how does that change the algorithm?
So the questions about the weight variable, I'm not prepared to even talk about that. we won't bother with it in this class. Okay, it's a more advanced use of linear regression in terms of what you can do with it. So we'll say next. We talked about a little bit last week that the 2 real options you have with multiple linear regression. The first one is to force the constant term to 0, meaning if all fields had a value of 0, what value would you want to predict? That is, it'll find that value. If we want to force that to be 0 for some reason, we could check this box. My advice is not to check the box unless you have a specific reason or know why you would. In this case, I have no reason to believe that that would help the algorithm or make sense for the algorithm, so I won't check it. It's possible it will find that the best thing to do is use 0, but I'm just not going to force it to do so. The other option you have with multiple linear regression is kind of hidden under this variable selection button, where you can tell it might be best not to use all the fields that I've told you to use. That is, you might find that something like, let's say, the passenger count isn't useful. There's no pattern to that that's useful to predicting airfare. In that case, this option says you may unuse variables that the algorithm deems aren't useful, that aren't predictive of the airfare. Again, you might have a particular reason or intuition why that would be better or worse. For this assignment in this class, I'm not going to require you to do one thing or the other. If you want to try it out both ways and see what it does, that might be instructive in terms of learning about multiple linear regression. But for this class, we won't bother or worry about why you do it or why you don't. it's one of those things that it's a craft skill. It's something you learn over time when you would want to use it, when you might not. It depends on the problem at hand more than anything. So the last thing I'm just going to do, I will generate a summary report for both training and validation data, and I'll generate the lift chart for the validation data and say finish. Okay. So here on the screen is just the summary data. Okay. And let's see. So it lists the variables I used as input, the one I used as output, the various possible parameters you can change the algorithm with. And then down here, you'll see, even though I told it, I didn't tell it to do variable selection or anything like that, it did find that it could ignore one of the two of all those dummy variables, which shouldn't be too surprising, because if you know this is not a vacation, then that implies that the other field means, right, each field is the opposite of the other. That is, so if you know the value of whether it's not a vacation, you can assume it's the opposite of whether it is a vacation. So there's no predictive power to using both fields, essentially is what that says. For the rest of these,
That's what the red means?
So the red here is just indicating it ignored that field.
Okay.
Because it realized that field was redundant. The information it carries is redundant with another field. That is, it's just the opposite of some other field. The things that are interesting to see are these coefficients. So this is the actual model. The model says that to predict airfare, you first start with negative 23, and then you multiply the coupon field by 10, add that to multiplying the new field by negative 1.7, and so forth. You're adding together these coefficients multiplied by that field value. That's how you come up with the airfare. Okay. What's interesting is you can look at these coefficients and say things like, let's look at this vacation. So when the destination is a vacation spot, apparently we want to subtract. Okay, so if vacation yes is of one value, we would effectively subtract 33 from the airfare, or our prediction of airfare. So it's cheaper. The pattern we found is it's $33 cheaper to go to a vacation destination than a not vacation destination. Okay, in general. Okay, that's the pattern, and so forth. So whether Southwest flies to that location, if they do, the airfare is on average $35 cheaper. Okay, we would multiply this by 1, subtract $35 from our prediction. Okay, and so forth. You can sort of see there's some indication of what the pattern is just by looking at these coefficients.
So the more coupons you have,
The more expensive the airfare. Right? We predict a higher airfare for a larger coupon amount, and so forth. Yes, question.
I was just following along, and instead of ignoring the slot dummy variables, instead of ignoring the intercept, is that just something that it might do based on the training data set?
So the question was, when doing it yourself on your screen, it ignored the intercept. I guess it zeroed out the coefficient for intercept. That's possible depending on, your partitioning. You probably randomly partitioned records differently than my computer did. And that particular partitioning found that there really wasn't predictive power in using an intercept. So depending on your partitioning, you'll definitely get different answers. In this case, a $23 difference from my model to a 0 in yours, is what it found to be best.
I guess it's not kind of a follow-up to that. So it's not indicative of an error if it decided to use both of the slot dummy variables?
Oh, okay. So yours also used both slot variables, dummy variables?
Yeah.
That's curious. A little bit surprising, but no, not necessarily indicative of a problem or an error. Again, it might just happen that it, depending on the partitioning and other factors, it found some predictive power to using both. Certainly, if you're going to, if say my model is going to subtract $17 for a free slotted airport and do nothing for a controlled slotted, that's not much difference than, say, splitting the difference and adding 8.5 for the controlled and subtracting 8.5 for the free. Does that make sense? I mean, you're talking about a $17 difference between controlled and free. Whether you're adding 17 to one, or you're subtracting 17 from the other, or just splitting the difference, probably wouldn't matter in terms of.
Subtracting 23 from one and subtracting 40 from the other.
Okay, so there's a wider spread maybe in some of yours as well.
But still subtracting 17 difference that between the two.
Interesting. Okay, yeah. I see what you're saying. So the difference between what it adds here or what it adds there is about 17 in your model and mine. So the last thing I'll point out before we talk about error rates is scrolling slightly to the right here. You'll see this R-squared and adjusted R-squared. Effectively, and there's a whole theory of statistics behind this, but effectively what R-squared means is how likely is the how likely a true model has coefficients like these. That is, what's the probability that a true model that would fit the data perfectly would also have these coefficients, the ones that we didn't select to be 0. And in this case, the R-squared value is 0.78, meaning there's roughly a 78% chance that this model is close to the true model, in the sense that coupons do matter to the airfare, in the sense that median income does matter to the airfare. Now, on the flip side, there's about 22% chance that one or more of these things really don't affect airfare. We just thought they did because of the data set we had. That is, there's a 22% chance that if you had different data, statistically, you would get a 0 for one or more of these coefficients with that data.
So it's saying distance doesn't matter.
Okay, so the comment was that distance doesn't matter. Now, this is one of those things. It's multiplying distance by a relatively small value, but distance itself is always a very large value, right? Number of miles versus number of, say, passengers. Those are on different scales. That is, you're talking about thousands of miles, but you're only ever talking about hundreds of passengers. Yeah. So unless you've normalized the data or you're taking into account different scale of values, I wouldn't read too much into the exact value of the coefficient. More so whether it's just positive or negative. Okay. So finally, we'll take a look at the error rates. So what you'll generally see is a very low error for the training data. That's the data we trained the algorithm, right? Picked coefficients so that it could predict well on the training data, right? So you'll see a relatively low error there. What you're really interested in is the validation data. That is, if we use the training data as the standard of the pattern for predicting airfare, how well did we predict airfare for data that we didn't train with? That is new data, the validation data. And what this says is, on average, we were, $22 lower than the real airfare. Okay, so we.
Percentage. That's.
Yeah, average error here is an actual unit of whatever you're predicting. In this case, $22. We predicted $22 under the real airfare on average for the validation data. You might say that's pretty good. I mean, if you could guess the airfare within about $22, that's not a bad model, right? Certainly if this average error was something like 100 or 200, you're not really getting very close. Finally, we'll look at the validation chart. And the validation chart somewhat confirms we are doing better than just guessing the average airfare. That is, we can pretty much always get closer to guessing the right airfare with the model than we could just guessing averages. Okay. Now we're not, the distance between the blue and the red here suggests we're not great at it, That is, sometimes we're probably overestimating, sometimes underestimating, but on average, we're getting better than that, the average rate or the average airfare. So the model is useful. That is, it's better than an average guess would be.
What's the axis where it says cases?
Okay, so the question is about the two axes. So in this case, the number of cases is just the number of validation records.
Okay.
So it's just saying for validation records, how much error do you have predicting all of those cases? So predicting the first, let's say, see if I can make this work. Right here, predicting the first 100 airfares. If you guessed average on every one, actually I think I have that backwards. Not error, but how close are you? If you guessed average on every one, you'd fall somewhere in this range. And I'm not sure exactly what this measure is.
Okay.
But using the algorithm, guessing the first 100 airfares, you're doing better, right? Noticeably better than that. Okay, so that takes care of multiple linear regression. Just for comparison, let's use another data mining algorithm. So we're going to do the same thing, predict airfare using the other fields, just using a different prediction algorithm. Okay, let's use regression tree. And like I suggested last week, for this class especially, just use a single tree. These other options basically try to find, are there multiple different trees that you can use and combine together to do your prediction to make it better. In this case, we'll just use one tree. That is, we'll assume there's one good pattern in the data for predicting airfare, as opposed to different patterns for some of the data and some different patterns for different parts of the data, and you can combine the patterns together. So we'll do single tree regression. Same thing as before, and since we'd already done it, it knew we're going to use all the fields to predict the airfare field. Again, there's a couple options for regression trees. You can normalize data. You can limit how tall or deep the tree can go and how many nodes you have to have at any part of the tree before you should stop splitting and stop, dividing records into two different groups. I would suggest, in general, just using default values for those. The reason they're defaulted that way is those are generally good enough values. Now, the scoring option, you could say use the full tree you built, or you could score by pruning and removing parts of the tree if that helps you predict the validation data better. Okay, so we might build one big tree for the training data that does very well for the training data, but that same tree might not do as well on the validation data. We might want to actually get rid of some of the tree nodes, that is, some of the ways we divide data.
So it's still going to build the full tree.
Yeah, so in this option, it still builds the full tree for training. It just starts from that full tree and prunes off things as long as it helps predict the validation data better. Yeah, before predicting validation, yeah. And then that's what we'll use as our scoring, how well we did on validation data.
The minimum error tree, then why would you want to use that? Since you're
Yeah, I was afraid there might be this question. The difference between minimum error tree and best prune tree, I forget. There's some mathematical nuance to the meaning of one versus the other. Effectively, they mean similar things, which is how can we take the full tree and prune it down to be the best it can be at the validation data. The way it does that is, I think, slightly different between those two options. I doubt you're going to see a large difference in the output one way or the other. They're very nuanced things, I believe. So we'll use the best prune tree. Again, we'll see summary reports and a lift chart. You can tell it to actually show you the tree. So I'm going to actually let it show us the full and prune tree so you can see what those look like. Okay. So on the summary output, again, it sort of summarizes the parameters and options we chose. and then it gives us an output of what it decided to do. So it looks like, first thing, it says, let's divide categories based on their coupon. And the split value is we're going to divide records into two categories, two camps. Those with a coupon of less than 1.105 and those with greater than 1.105 coupon. Okay? And then so forth. Between those two cases, we split those based on first Southwest, and the other group we're going to divide based on vacation, and so forth. So you can see all the different ways it decided to split the data. That was the full tree. The prune tree, somewhat shorter. Again, it obviously starts the same place. First divide by coupon. Then for those with a coupon less than 1.105, divide on Southwest. For those with a coupon value of greater than 1.105, divide them based on vacation, and so forth. There's the minimum error tree. And then finally, our error rates. So again, you'll see a low error for the training data because obviously it's building the tree to predict the training data from the training data. And then for the validation data, we see something different. Now in this case, the average error on the validation data is 2 or 2.6 dollars. So again, this is saying the classification tree on average predicts an airfare that's $2.6 higher than the real airfare, right? Closer on average than our multiple linear regression, which was $22 under. This one is $2.6 over on average. Yeah, question?
RMS error.
The RMS error, so the question about the RMS, it's basically taking all the errors and squaring them so that whether you're overestimating or underestimating, it wouldn't matter because it squares the value, and then it's basically averaging those squared values. What that means is, obviously the lower the better, but you can't take this amount directly and interpret it as dollars or how off or close you are because it's been squared and then square rooted and other things. It's not the same as average error, but you use it the same way just to say lower is better. Lower is getting better results. Yeah, question?
So if we want to compare two algorithms, and we want to, rather than eyeballing the lift charts, sometimes you can see a definite difference, but if it's pretty close, can we just compare the two RMS error values and determine?
Yeah, so the question is, when comparing two algorithms, you can obviously use lift charts, but if they look similar, certainly you can come look at the error rates, and say, well, which error rate is better? Now, did you happen to do this same thing?
Yeah.
Okay, so for your regression tree, what average error did you get for validation? Just curious.
$2.64.
Okay, so you got something very close to what I got.
Yeah.
Generally speaking, if you ran that and I ran it on my machine, depending on how data was partitioned, we might have been off by a little bit, right? I might have been off by $2.6. You might have been off by just $2. So I wouldn't put too much meaning into the error rates if they're close when comparing two algorithms. That is, if they're only off from one another by maybe 10%, that might just have been because of the way the data was partitioned. If they're off by 50%, like one's twice as good as the other according to error rates, that's a pretty good indication it's probably in general just a better algorithm for that case, for that data.
Well, I guess.
So the answer being, if the lift charts look very similar, you can come look at the errors, but if the errors are also pretty close to one another, then you can't definitively say, oh, one is definitely better than the other. It just happened to be better with that partitioning and the way it's set up. If we repartitioned or ran it on a different machine, you might have got opposite results. Still close, but just the other one seeming better.
I guess what I was thinking about it is I did k-nearest neighbors and regression trees when I was doing the assignment.
Okay.
And I didn't know how to interpret the RMS error values, so I just was flipping back and forth between the lift charts, and I saw a very slight bump in one, and I was like, well, that's kind of
okay. Yeah.
to say that.
So if you can visibly see a difference in lift charts, that's probably an indication. It's an indication that one did better over the other. If that visible difference is very close, I mean, it's not a lot. Again, that's probably evidence that both algorithms have done almost equally well, and there's not one that's just definitely or certainly better than the other. So the answer of whether one is better than the other might just be they look pretty close. There's not conclusive evidence to say one's doing that much better. And that can be based on RMS error, average error, visibly on the lift chart. All three of those things are telling you slightly different things about how wrong the predictions were. For example, because this root mean squared error is squaring errors, it's much worse in terms of this error if you're off by a lot, maybe over-guessing one by a lot and then under-guessing another one by a lot, okay? Because it's going to square those differences. Whereas if you over-guess one by a lot, under-guess another by a lot, in terms of average error, that error averages out very small, right? And so the average error is basically just telling you on average, how off were you, but you might have been overestimating some records and underestimating some records. It just averaged out to 0 or close to 0. The root mean squared error will give you a better indication of how off really was I, not being over or under, but just off. How off was I? Now again, you can't say I was $41 off. The units of this are undefined. But definitely you see the root mean squared error will tell you sometimes a different story. You might have a very low average error, but a very high squared error. And all that means is your average error being low just means when you were overestimating, you compensated by underestimating somewhere else. Okay. So you're averaging small errors by compensating large positive errors with large negative ones. The squared error being high would help identify that.
Okay, so you aren't looking for us to take all of these different things into account, because when we were doing classification, it was much easier to kind of see the output and say, the output was a little bit easier to kind of look at.
Sure. Yeah, so for classification, it's generally it's easier in terms of you're talking about percentage errors. Right. Percentage, because you're classifying into one category or another, and you're either right or you're wrong. There's no degree of wrongness. That is, you can't be highly wrong or slightly wrong. You're just wrong or not in terms of classification. Prediction, there's a little more to it. You could, like I said, you can be overestimating but then underestimating to compensate to get a low average error, but you're still getting bad error. I mean, it's not a good model because you're always either way overestimating or way underestimating. Neither one's desirable. So there's multiple factors to consider. In terms of the assignment, I didn't need you to do that full of an analysis. I just wanted you to be able to run two algorithms and use one of these measures to tell me why, based on that measure alone, why one algorithm might be better than the other, or they might be equivalent or close to the same. Okay, so last thing, let's take a look at the lift chart for regression trees. So this lift chart looks pretty close. I'll switch back and forth. There's the regression tree lift chart and the multiple linear regression lift chart. They look very similar. That is, they're both definitely doing better than an average airfare guess, though they're certainly not perfect. No prediction probably ever would be, but they're doing roughly probably the same better at prediction. In terms of the error rates, if you remember, let's find the regression tree output. So on average, the regression tree was $2.6 over estimating on average, with the root squared error of 41. Multiple linear regression was under, on average it was under by $22. Okay. Seems like a big difference, but the root squared error here is pretty close. Okay, probably all that means is the regression tree, since it has a lower average error but a reasonably high root squared error, it's just overestimating one record by the same amount it underestimated another one. Right? It's just always over and underestimating by equivalent amounts. So the average comes out low, the squared comes out, medium, I guess I would say. Multiple linear regression, same root mean squared or close to it, higher average, which probably just means multiple linear regression is always underestimating. Right? So even its average is a relatively large, compared to regression tree, relatively large negative value. It's just, on average, it's always $22 under. It's not bouncing between over and underestimating on records. It's just always being underestimated. Okay, that's a simplification and an assumption I'm making based on these two measures. You can certainly dig deeper into it, but
So how do you
that's one explanation.
How do you use the data?
Okay,
now I
so
want to know. Hey, I'm flying from here to
okay,
Miami.
so the question now is how would you actually use this? The good news is the two models I selected are very easy to do so. The multiple linear regression, you have the coefficients here. All you need to do, if you wanted to predict the airfare for some new flight, you just have to figure out what's the coupon number, what's the what are the values for these fields, multiply them by their coefficients here, and add up the result, and that's your prediction. In terms of the regression tree, what we didn't look at yet is the regression tree here. So this says, every airfare, you first look at coupon. If it's less than 1.105, go over here to the left. If it's greater, go over here. And what you'll see is, for a new airfare you want to predict, you just follow the path through this tree. You'd say, okay, is the coupon rate greater than 1.105? Oh, it is? Okay, go this side. Okay, now I look, is it to a vacation spot? Maybe no. Okay, so I go to the left. Is the distance less than 1298? Maybe, yes, it's less than that, so I go to the left. Then you'd say, okay, does Southwest fly there? Yes, it does. Okay, go to the right. I'm going to predict the airfare is $130.30. That's what this says. So literally, the regression tree is just giving you sort of a prescription of questions to ask, and depending on your answers, you go one place or another until you get to the end, and then that's the prediction, the predicted value. It's saying records that follow that pattern seem to have an airfare around, or the averages, to about $130. So that's my prediction. Records that follow this other pattern may over here end up having an airfare closer to $212.
Down Southwest on that side.
Yeah, so yes. So the question was, it's pruned out Southwest one place. It's not necessarily true that once you split, you will necessarily want to split by the same thing on both sides. So even here, depending on coupon value, you might then want to divide based on Southwest flying there. Otherwise, you might want to divide based on vacation. Right? So the patterns can be complex. Depending on which branch of the tree you're looking at, the pattern may ask different questions. But this is what tended to predict best values. Yeah. So those two models directly give you something you can use to predict future values. K-nearest neighbors, unfortunately, is not. Right? K-nearest neighbors just tries to figure out, okay, which K training records are closest to the one I want to predict. That doesn't give you a visible indication like these two things did, or a table of information like these two did, for you to predict new records. Okay, I guess theoretically, if you wanted to, you could say, all right, let's go find the K closest records to my one I want to predict, and you'd have to, by hand, calculate all the differences, pick the K nearest ones, and then average their airfares to make your prediction. That being said, K-nearest neighbors is not a good model to use on future data by hand, right? You'd really want a computer to do that work for you. Multiple linear regression, and especially regression trees, build and represent their model in a way that even you by hand can quickly utilize it. You can put in your own data or visibly look and use those models to make your own predictions. Yeah.
Cool.
All right. Question?
It's kind of more of a tool question. I noticed that I partitioned before I inserted my dummy variables. And
Okay.
then that required me to partition again because it said it didn't have a training validation set difference. Does that make any kind of difference?
Yeah, so the question was, you instead of transforming first, you partitioned first and then transformed. For whatever reason, this particular software, when you transform data, it seems to lose the partitioning. So you'd have to partition after transforming. There's not a reason why that is. I guess that's just the way the software works. But yeah, you transform first, then partition for this software. No reason other than that's just the way they made it, I guess. Okay. Hopefully that gives you enough information. You can at least complete the first assignment and gives you a better idea of data mining, how to use it, especially how to analyze results. Okay. I did want to look just briefly and make sure I addressed all the questions from the assignment. Let's find. Thought I had the assignment already. There we go. Okay, so question or part A, in which field is, or which column is the field with the airfare amount? So just literally coming back to the raw data, the airfare here was in column R. If you wanted to count that out, I guess you could and tell me which field. So that's all I was asking is airfare, just looking at the data sheet, which column was that in? Okay. Let's see. How many records are there in the database? You can simply look at just the number of rows. Yeah, so 639 rows, but you have to remember the first row has the field names in them. So 638 records, technically. So if you forgot to subtract that one, you can go back and do so. Resubmit your assignment. What is the minimum, maximum, and average airfare amounts? There's various ways you can do it. One of the ways, at least, you can highlight all the airfares, and it gives you down here at least the average. So the average value for airfare was $160.88. You could similarly, you can use Excel functions like min. So I want the min of all records from R2 to R639. So the minimum was 42. There's other ways you can get to it. Yeah, if you highlight records, I think you can change what's displayed here. So it's giving me average, count, and sum. You can have it tell you min and max, and many ways you can go about getting the information. You could sort. So if I just wanted to sort, so the minimum airfare is $42.47. The maximum's $402. No right or wrong way. Just mainly there was a question to make sure you could use Excel, to read data out, sort or use functions or whatever it takes. Okay, so then part D is making the algorithm. We did that, or using one of the algorithms to make a model. Part E, explain why we partition first. So we've been over that last week especially. Make the model, discuss, or two models. So we did that with multiple linear regression and regression trees tonight. And then compare the results, which we've done. You can compare visibly the lift charts and tell me lift charts look relatively the same. They're both doing roughly the same amount better than an average guess. You can do it with the average errors, in which case you could say something like, it seems the regression tree comes very close in its predictions, within about $2.60 on average. whereas multiple linear regression seems to generally underestimate by about $22. You can look at square or root squared errors and say those two being very close. The models are generally predicting with the same amount of error. Okay, whether one's over and under predicting and the other's always under predicting, or whatever the pattern is, they're both predicting the same rough error on average, same amount of error, I guess I'd say. Any of those answers or combinations thereof would be acceptable. All right, any final questions about assignment 1 or data mining? Okay. Well, let's go ahead and take our first break for the night. So we'll take about a 15-minute break, come back at 7:20, according to the clock on the wall, and we'll start talking about short-term forecasting.